Okay, this is chapter 11, problem 6. So the basic setup of this problem is that you've got a spider web in which a fly is caught. So we should probably draw a very cool spider web. And it looks something like... yeah, I'm pretty good at drawing spider webs. Okay, anyway, kind of like that. There's a spider here. All right, the point is we're not even going to use this because the thing is the spider web, although it isn't a spring itself, it has a springy-like behavior. And so what we're immediately going to do when we think about this fly caught in the spider web is we're going to translate this to a picture we're more familiar with, which is to say you've got a spring with a spring constant K and a fly with a mass M, and effectively this K will describe the springy nature of the web. Okay, so this is, if you like, this is our picture. All right, and we're told some information. We're told that the mass of the fly is 0.22 grams, and we're told something else. We're told that the frequency of oscillation, that is to say, how many oscillations per second does this thing undergo, is 4.0 hertz. And remember, 1 hertz, this is the same as 1 per second. Okay, we want to know in part A, what is the effective spring constant for the web? Okay, so at least conceptually, let's think about what we have going on here. Concepts. We have spring-like motion, mass and spring-type motion. So if you like, this falls under the category of simple harmonic motion, which also might just be abbreviated as SHM. For which there is really one formula. I suppose there's 1.5 formulas. The one formula that you need to know or have on hand is that for a spring, or anything that behaves like a spring, the period of motion, t, for a spring is given by this equation, 2 pi times the square root of the mass of the object connected to the spring divided by the spring constant. Okay? So that's the main equation that we need, but we also want to remember how to relate period to frequency. And so that, if you recall, frequency, F, is given by 1 over t. Okay? Frequency, again, has units of hertz or 1 per second, and period has the units of seconds. So that's why they are inversely related. All right, part A, what is the effective spring constant for the web? And so we're going to have to use this equation here. It has the spring constant in it. It's the only one we have to use. We have a mass. That's good. We don't have a period, though. We have the frequency. So if you like, what you can do is simply invert this frequency in order to find the period. In other words, this is another way of saying this is that t is equal to 1 over f. So we can do that. Instead, I want to kind of put these together because we're going to need to use, or it's going to be convenient to use a combined equation in part B as well. So let me point out that if the frequency is 1 over the period, then that means the frequency of a spring, 1 over the period, it's simply 1 over this whole quantity. In other words, 1 divided by 2 pi square root m over k. You can pull out that 1 over 2 pi, and then what you have is 1 over a square root which has a fraction inside of it. What you do is, remember, when you divide one thing by a fraction, you end up flipping that fraction, whether there's a square root or not. In other words, this is the same thing as a square root of k over m. Okay, this is literally the inverse of the period. I suggest we use this. And now for part A, we want to figure out what is the spring constant. Why don't we use this equation to solve for it? Best way to do that, I think, when there's a square root, let's get rid of that by squaring the entire equation. So f squared is equal to this thing squared. In other words, 1 over 2 pi quantity squared, and the square of a square root is just k over m. I'll multiply both sides by the 2 pi quantity squared and by m, and so I guess that what that means is that 2 pi quantity squared, or 4 pi squared, times m times f squared, that should be our spring constant. If you like, that's a master formula that we can use. The mass is given, it's in grams. We had better convert that to kilograms. The frequency is already in the right SI units, so we're almost there. This is apparently 4 pi squared. The mass is, let's write this as 0.22 Remember that 1 gram is 1/1000th of a kilogram. I'm proud of myself for saying that right. 10 to the minus 3 kilograms. And the frequency is 4.0 hertz, or if you like, 4.0 times 1 over seconds squared. When you work this through, you should find this is 0.13896, or approximately 0.4. Wow, sorry, 14. And the units are kilograms per second squared. And it's technically not incorrect to write it this way, but this is a confusing way to write it because what's the physical significance of mass per time squared? Confirm for yourself that this should be the equivalent of a Newton per meter, which has much more physical significance, which tells you an amount of force per unit distance. Again, that's what should happen with a spring. Remember, the spring constant tells you for every so many meters that you push it or pull it, what's the force that you get out of it. So this should be the right unit, and that should be the answer for part A. Part B, you're asked to determine if it's a different mass of a fly. If there's a mass, let's call it m prime, equal to double it, 0.44 grams, then what is the frequency of the oscillation then? What is the new frequency? Let me call that new frequency f prime. Now, a straightforward way to do it would be to simply use this formula from above. We have our spring constant, and all we would need to do is plug in the new mass. But I want to show you a slightly different way to do it, as you can see how things scale. Let's see. What would we do? F prime, you can use this equation, 1 over 2 pi, square root of k, and the only thing that changes is the mass, right? I don't put a prime on k because the spring constant, if you like, the web is left alone. I want to do something though. I want to divide this equation by f, the original frequency. And you may wonder why I would be motivated to do that, because I can just use this formula after all, and you can. But verify that if you do this, the 1 over 2 pi's will then cancel. In fact, the k's will cancel. This has a 1 over m prime in the numerator. This has a 1 over m in the denominator. This turns out to be m over m prime. And since the old mass is 0.22, the new mass is 0.44, this is actually the same as 1 over the square root of 2, or square root of 1/2. That may be useful for you, not perhaps in this problem, but in some other problem. What we learned then, this tells you that f prime is simply 1 over root 2 times f. In other words, 1 over root 2 times 4 hertz, which is approximately 2.8 hertz. Okay. For our final answer. Lastly, as a sanity check, we should ask, does it make sense if you put a more massive object here, what should happen to the frequency? What should happen to the rate at which the thing oscillates? My experience tells me that when I put a more massive object, it doesn't wiggle quite as quickly. It wiggles more slowly. In other words, it gives me a frequency that is lower than the original. So it seems to make sense.